Now we have our next speaker, Ilya Girgorik, and Ilya gave a really awesome talk at Ruby Conference last year, and he was one of the first people I thought of for presenting at our conference here, and I'm really glad that he's able to be with us, and he's going to be talking about how to build your own proxy in, 5 lines of code or something like that?
I don't know about 5.
Okay. But here, I give you Ilya Girgorik.
All right. All right, thanks, guys. Is this thing on? Yes, it is. All right. So when Josh first approached me about giving a talk, right at the time, I actually found a new favorite hammer, and it was a proxy server, which I had written in Ruby. And really, everything that I was doing at the time for about 3 weeks, everything looked like a proxy server. So I just wanted to talk to you about some of the cool stuff that you can do with proxy servers, and maybe not get into the low-level details of how to do it. I'll actually walk you through the code to show you how you can do it, but then actually focus on the kind of high-level patterns of what you can do with proxy servers. So first, by way of that did not work. Let's try that again. It's changing on my screen. There we go. All right, so first, by way of introduction, I'm with a company in Canada called AutoDriver. We have this web service called PostRank, which if you guys can associate with information overload, you should give this a try. We have a couple of really interesting solutions for filtering RSS. But more importantly, the message that I want to send here is this is not purely theoretical. We actually use this stuff in production. So it's actually production ready. Some housekeeping before we actually get into stuff. You can actually find the slides online. There's my Twitter account, my blog. So let's get right into it, right? Proxy servers. We all love them. We all use them. There's a lot of different solutions for proxy servers. There's hardware. There's software. If you look at hardware, there's F5, kind of the big guns and all that stuff. And then you get into the software versions, which we can find proxy servers for virtually any application out there. So there's MySQL proxy, which allows you to do all kinds of crazy and awesome stuff with load balancing your queries or sharding them on the fly. Really neat stuff. HA proxy is kind of a generic TCP layer. It'll do anything you want with a TCP stream. And then you have stuff like Apache and Nginx, which I think we as web developers are all really familiar with. It's the concept of the reverse proxy. So on that note, I think one of the reasons that the reverse proxy is extremely popular, or at least we all know it today, is this myth of slow framework. So insert your favorite one, right? Rails, Scala, whatever the flavor of the month is. And I think the reason for that is, as web developers, we tend to fixate on the stuff that we're currently working on, which is the application server. We like to think everything is encapsulated in your Rails application. But in reality, when you do the profiling, it turns out that most of the time is actually spent in the database. So the common response of the PHP guys, for example, is there's no reason for us to make PHP any faster because we end up spending most of our time in the database anyway. Or at least that's the answer that they give at Yahoo, which I think is largely true. But the reality is, framework or not, you do have the problem of application servers and threading, scheduling, all that kind of stuff. So more often than not, we need more than one application server to actually make our apps run, right? So we end up implementing reverse proxies with Nginx and all that kind of stuff. It's really exciting to see Passenger take off and just kind of eliminate all that extra work. But there's still plenty of cases where proxy server is the perfect solution. So one of the really nice things about having a proxy server is the horizontal scalability that it gives you, because it allows you to abstract entire services of any number of application servers behind a single endpoint. So it's all nice and clean. Of course, then you get into crazy schemes like your application is growing, so maybe you're going to shard it by geography or maybe a different data center, all kinds of cute stuff. And this is pretty neat. And the 90% use case of all the proxy servers that I think we use today, and what we think of when we say proxy server, is what we call a transparent cut-through proxy. So first of all, transparent means that it's not visible to the client. When you make a request to postrank.com, for example, you don't actually see that you're passing through 3 layers of proxy servers to get to the final destination, unless that proxy server actually injects some sort of a header, and the only way you can get at it is to request and look at the headers. So for the most part, it's completely transparent to the user. And then the cut-through property is really nice for performance, because it means that the proxy server does not have to cache or buffer anything when the request is coming in. It can just pass it right directly to the app server, so it can just stream it. So essentially all it is just kind of, it maintains state as to where the request is going and continues forwarding that data. It's pretty nice. And at the end of the day, this is the 90% use case for all of the proxy servers deployed on the internet today, right? It's the super useful scalability tool for horizontal partitioning your workloads, all that kind of stuff. And this is awesome, but what I want to talk about today is that remaining 10%, which I recently discovered for myself, and I think it's really, really interesting, and in some way, the success of the 90% has kind of overshadowed all the possible awesome things we could do with the 10%. So first of all, a little bit of background. How did I get on this proxy route? It actually started with the problem of having to set up a staging environment. And I say problem because, let's face it, it's a necessary evil. You have to do it. You can't live without it after you reach a certain point. But it sure is annoying as heck to set up. And it's expensive to maintain, right? And the reasons for that, I think, are because, first of all, it's duplication. So if all you have is one Rails application that's nicely encapsulated on a single server, it's not hard to bring up another one, and then you have your staging environment. The problem surfaces when you actually have multiple services, or in our case, we actually have maybe 20 or 30 services, which are deployed across maybe 15 or 20 machines. How do you stage that? Right? You either have to bring up a completely parallel environment, which is both expensive and painful to do, or you just kind of wing it and just hope for the best. So duplication is definitely a pain. It's expensive, though. You have to test your stuff before you deploy it. And then actually the biggest pet peeve of mine is this simulating traffic. This is a recurring problem that I find. It's annoying because first of all, what does it mean to simulate traffic? What is a real workload on your servers, right? How do you record that? So first of all, somehow you have to capture all that traffic, and then you have to record it somewhere and replay it, right? So how do you replay it? What about Saturdays versus Sundays, all that kind of stuff? What about a week from now when you deployed it, when you got some coverage somewhere and the profiling of your workload has actually changed? All of a sudden, all of your nicely stashed away scripts for simulating traffic are completely and utterly wrong. So this was a big pain that we had in terms of just staging was a recurring problem that we had to fight with, and it basically became a huge overhead cost for us, right? Anytime the profile of the queries is changed, you got to redo it. The load changes, you got to redo it. Parallel environment in our case was another 15 servers. That sucked. Slower release cycle because we couldn't actually test our stuff fast enough. We actually had to set up the environment because we couldn't maintain 15 servers all the time. We actually had to bring up 15 servers to test our stuff before major release and then shut them down. That's no good. So around that time, I actually ended up creating this AutoPerf script, which, if you guys are familiar with HTTP perf, it's probably one of the best tools for actually simulating load on your application. So if you have a Rails app or any kind of RESTful API, it's basically a driver. You can give it a text file which supplies the query string plus the URL. You can actually give it a time as well, so you can time the queries. You can actually say, at second 1 do this, at second 2 do this, then wait for 5 seconds, do something else. You can also do post queries. So in the same file, you can actually record a post body and then let it replay. So it's a really nice tool, but the problem was it just does one run of that and it quits. So this AutoPerf driver, really, really simple script, basically automates just iterating over a collection of different concurrency levels, and then finds out what is the actual performance curve of your application server versus number of clients that's being connected and what's the throughput, so you can actually graph it. And that was great, except there's a major problem here, and that is how the heck do you actually get that file of all the requests? How do you assemble that? One of the ways we did that was we actually started injecting our custom loggers into our application servers, and we would record the stuff that would come in for some period of time, dump them to a text file, and then say, well, here's a representative load based on 2 weeks ago, so we're just going to replay that against the new service, which was kind of cool. It worked up to a point, but it became a pain nonetheless. So then came the big aha moment, right? And this is where the proxy server came in. And it was, instead of actually simulating the entire environment, why don't we just inject a proxy in between? And we're actually looking for a tool to do this for a couple of months, and it never occurred to us, for some reason, to actually write our own. We're always, because it seemed like it's a hard thing to do, right? When you think about proxy servers, they got to be fast, it's got to be written in whatever it is in C, use KQ and EPOL and all that kind of stuff, all the big words. And it just seemed hard. And then at one point we turned around and said, well, hold on, we implemented all of our stuff in the Invent Machine anyway. We're pretty good at this stuff, so why not give it a try? So, hold on. This is silly. There we go. So a couple of hours later, probably 2 or 3, this is what we had. And it's pretty simple, and I think you actually get the point just by looking at this piece of code. There's all this piece of code does is set up a proxy server which listens on port 9000 on IP 102.1.0, and it duplexes the request to 2 different application servers living on 2 different IP addresses. And the reason you can't actually find this in your run-of-the-mill proxy servers is because when you build a proxy server, you tend to just send the request to one. You never have the need, really, to send the request in parallel to 2 servers and then only return 1, right? So that was, we either had to go in and modify something like HEProxy, which is no fun, or we could build our own, and this is it. So this is actually the actual output of the first prototype that we built, and you can actually see at the top the responder in the benchmark. The responder is our production server, and it returns in 1 second or so, and the benchmark returns in basically 1 second as well. And then it actually gives you the difference in the response time at the top, which is, in this case, the benchmark was actually faster by just a small fraction of a second there. Second request was slower, so on and so forth. But one interesting thing here is the first 4 requests were actually all the same. They returned all the same data. And then the last one actually returned something different. So we spit out the actual output of both of the application servers for us to look at. And so in this case, one of them returned Hello World 0, and the other one returned Hello World 1. So, of course, the neat thing is this is done in real time against production traffic. It's transparent to the user, so that the user does not see a thing. And what's even better, they don't actually even see a performance hit on this, because we were smart enough to implement it such that it doesn't. So the code for this demo, you can actually download it. It's EM-Proxy. I was extracting it on the plane. I didn't get very far, but the demo is there. You can run it. I'll put up more documentation on it, and basically we'll actually walk through some of the code in the next couple of slides. But I really, really encourage you to take a look at the lib directory here and just play with it, because all it is maybe 300 lines of code, of event machine code, and it gives you the framework or a pattern for how you could think about building these proxy servers. So in terms of the high-level concepts that are going on in the EM-Proxy, there's 3 basic steps. The first one is the accept connection state, which is not unlike any other web service. But then the difference is you connect to two different endpoints, a production and a staging. And unfortunately, these are actually hard-coded in the EM proxy right now as variables like that. So we just need to extract it a little bit. The second one is you want to stream the response to the client from the production server, right? You're going to get two streams of response back from both your application servers. So you need to mark one as a production and then return that back to the client. And the second one, you can do whatever you want. You can either buffer it, you can discard it. That's up to you. And then in the last step, what you want to do is actually do some sort of analysis on it. So you can say, this guy returned in 2 seconds, this guy returned in 1 second, so yay for our new application server because it's 2 times as fast. So before we actually jump into the code, how many people here have actually used Event Machine? Familiar with Event Machine? So maybe 20, 30%-ish. So this is a one-slide crash course on Event Machine. So you guys will have to kind of trust me a little bit on this stuff. But I really encourage you to take a look at Event Machine. It's a really exciting project. There's lots of work going into it right now. And there's a lot of companies that are using it in production as well. So it's definitely production ready. To start to build a service in Event Machine, all you need is the bottom block, EM run. You declare start server, give it an IP address, a port, and then you give it a class, and you're up and running. So in many ways, not unlike rack, except slightly different semantics. And then to actually implement the class you inherit from EM connection or extend EM connection, and you basically have to only think about 3 methods: receive data, unbind, and connection completed. The only other one that you need to know is send data, which does exactly what it sounds like. Receive data, once again, same thing. So you get pieces or chunks of data streamed to your client. Unbind is called when a connection is terminated. So if the client closes the connection, the unbind will get called, so you can inject some code in there. And connection completed is actually for clients only. It's when you try to connect to an IP address, when that connection is negotiated, and when the TCP handshake is complete and all of that, that gets invoked, so you can start performing whatever it is that you need to do. So that's Event Machine in, I guess, 10 words or so. And I really encourage you to take a look at it. So now getting into the actual code, there's 3 different classes that we're going to take a look. The first one is the actual Duplex, which is the very, very basic implementation of a Duplex proxy. As you can see, we have a receive data method, and all it does is called proxy data. And instead of just sending to one other client, we just declare a responder, which is our production client, and then we have a benchmark, and we just stream the data right to them. And then the opposite of that is the relay data from backend. So now that our application server has received data, we're going to take that data, we're going to take the response and stream it back to the client if it's the responder that's sending us the data. And then finally, when everything is done, we're going to call some code to terminate both of the connections so we don't leak connections, and call some sort of a process method on it, and then unbind to terminate the connection altogether. So I've omitted a little bit of code in here for the sake of clarity, but this is basically all it is to the Duplex. We're just splitting traffic. The actual proxy is the connection that gets made to one of the backend servers. One interesting concept that's available in Event Machine is deferrables. So what you can do is you can actually instantiate or give it callbacks and then declare deferrable succeeded, and then the callbacks will get executed. So the reason we want this is, let's say a response comes into your proxy server, you start opening connections to 2 different backends, but the data is already streaming. So what you want to do is you just want to push the data into some sort of queues, which is basically what the callbacks are. And then once you actually establish the connection to the app server, you just call it succeeded, and then all of the data gets immediately pushed to the app servers. So it's just a neat pattern. So it avoids having you to buffer data in your initial connection class. So here we're doing exactly that, where when we initialize the connection, we declare a new deferrable, and then when the connection is completed, which means that the client is connected, we call it succeeded. We have send data, which is what we call in the original Duplex class. And here, as you can see, we're doing the connected.callback, so we're just passing data in. That's what will get streamed to the clients. And then we have some maintenance stuff for unbind, so terminating the connection and receiving data from the proxy. All right, and then the last piece of code, which is completely kind of up to you as to how far you want to take it, is the actual PostProcessor. This is where you can actually do some interesting analysis on everything that's just happened in your system. So in this case, both of our connections are already terminated, so what we're going to do is call a process method, and in this case I'm doing some time analysis, and I'm going to process the bodies of both of the responses. If you guys remember that a couple of slides back, we spit out the diff between the two. So that's what's happening here. This code is kind of silly, but all it does is prints out a green or red time difference, essentially. So completely extensible, and you can do all kinds of stuff. So this is kind of cool, right? It's cute. That's the first thing that came to my mind, but who cares? This is yet another web transparent proxy that, it's neat. But this is where the fun begins, right? This is where you realize that you have a giant hammer and you can apply it to all kinds of really cool stuff. What we saw here is the transparent proxy, but who said that it actually has to be transparent, right? We can inject some really cool stuff in between. We can do caching, we can do validation, we can do intercepting proxies, and this is where all the exciting stuff happens. So first of all, validating proxy, right? So the next step that we took was, instead of just passively looking at the data, we actually know what we're getting back from our API servers, so why don't we customize it? So in this case, we know that we're getting JSON data back, so let's parse that and diff the bodies, right? So in this case, we actually had two different API servers that return a rank for a website, and production said that Vita.com, which happens to be my blog, was previously 8.2, and then in benchmark it's 1.0. Clearly a bug, right? So we got to fix it. So once again, we can inject this right into midstream into one of our application or production environment, and then compare the performance in real time. So that's kind of cool, right? Validating proxy. And then if you remember this slide, right, we're proxying data to the responder and benchmark. The transparent proxy will just pass the data right through, but who said you can't actually touch the data? You can do all kinds of interesting stuff with the data at this point, right? And if we look at, think of some examples, this is just three I came up with as I was making the slides. Nobody said that this is HTTP traffic, right? This is TCP. So we can inject this in between SMTP servers and actually, I don't know, play with it, implement our own spam detection. We can encrypt or decrypt data. Like for example, if you are storing files in S3, you could put this guy in front and then decrypt or encrypt on the fly. Seems kind of like an interesting application. You can even do MySQL sharding logic if you really wanted to. I mean, that would be crazy, but that would be pretty awesome too. So a quick example and walkthrough of an actual example where we use this at PostRank. How many people here are familiar with Beanstalk? Awesome. So maybe 50% or so. So Beanstalk is a distributed in-memory work queue. It basically allows you to set a job and say, at 5 o'clock today, put this on the queue such that when somebody requests it, it's available for consumption. Or so you can push it into the future, you can set a priority on it, all kinds of interesting stuff. So what do we do with it? We had a use case where we actually needed to store 80 million jobs in memory. We do a lot of RSS fetching and updating metrics and all of that. So we have 80 million jobs that we need to do. And if you do the math, the overhead, it turns out that the overhead of any Beanstalk job is 93 bytes. We needed roughly 300 bytes of additional data just to pack our stuff into that. And if you do the math, it works out to be about 30 gigs of memory, which is equivalent to 2 extra large EC2 instances, which are 16 gigs each. And I don't know about you, but that's pretty expensive, right? It's $1,600 or so just to store 80 million jobs in memory. And unfortunately, as awesome as Beanstalk is, it doesn't have any kind of disk-based fallbacks, so it's all in memory. That's how they make it fast. So some observations that we made in the process, though, was 80 million jobs is great, but each one of our jobs is rescheduled. We have a job that's repeated at intervals, so we'll check. Let's pick an example of an RSS feed. We just check the feed. We're going to check it again in an hour, so we're going to push it out and wait for that to pop up back in the queue. So most of the memory is actually wasted. And then the other problem is, of course, that Beanstalk does not give us any kind of overflow to disk. So even though we have 80 million jobs, 95% of them are just sitting there idle, they're not ready for consumption. They're just there because it happens to be in memory. So playing with this idea, we came up with a very simple architecture and an extension for this, where we said, well, why not just build an intercepting proxy in between? If Beanstalk doesn't want to give us persistence, then we can inject our own persistence into the protocol. So what we did was built an event machine-based proxy which intercepted some of the commands and shoved them into MySQL and then passed on the others. So a quick walkthrough through the code. I don't know if you guys can see that. No, you can't. So that's really hard. Beanstalk uses text-based protocol. So just like Memcache, there's a set and a get plus the size of the body and then followed by the actual message. So it's really, really easy to parse and extend. All you need is a regular expression. If you guys take a look at the slides after the fact, I'm sure you'll be able to see it better here. We just have a regular expression right at the top, which we define as a new command, archive, and then specify the priority, all of the regular Beanstalk variables, and then a body. And then in the next step, whenever we get data, we just called parse request, which executes the actual regular expression against the packet that we got. And if we happen to detect that we're sending a new command called archive instead of a schedule, we populate the job. We buffer it actually until we get the entire response, because it's possible with Event Machine you're getting your 4 kilobyte or 16 kilobyte, depending on what your kernel is set at, chunks of the body. So we have to buffer the entire request. And then once we're done, in the very last step, we just call to MySQL directly and say, archive this, right? So whenever we schedule a job, once that job is complete, we call archive. It gets passed back to this client. It gets put into MySQL, and then later we just take it out of MySQL when it's ready for scheduling, or maybe 5 minutes before it's ready. Stick it back into the memory queue, and we're good to go. So essentially, this is what we ended up with. This is completely transparent to the client. So if you guys have used the Beanstalk client library, you wouldn't even notice a thing if you were going against our Beanstalk implementation. We called it the Chronos scheduler, and we essentially just added a new archive command. And in the end, we ended up opted out for implementing a new command as opposed to extending an existing command, because we added more additional features after the fact. So we didn't want to overload an already existing command. But you could have done that as well. What we could have done, and this is what we had in the first implementation, was if there's a job, if we were scheduling a job more than 30 minutes into the future, we would just store it into MySQL as opposed to into the memory. So all of this allowed us to severely cut down on the memory use. Right now, we can run the whole thing on a small EC2 instance. We just chose to use a larger instance for performance reasons. And even better than that, it's completely extensible. We've actually extended the protocol quite a bit by adding job keys and all kinds of interesting concepts that we needed, that we've been pushing the Beanstalk guys to do for maybe 8 months now, but they're just not getting around to it. So we just injected an intercepting proxy and built it ourselves. And at the end of the day, it's one proxy, one Beanstalk, and MySQL, and it's serving about 200 requests a second. So the performance overhead is maybe 5% based on our benchmarks. So this is just a great example of injecting functionality into a place where none really shouldn't have been. So you can do all kinds of crazy stuff with this pattern. And I would really actually encourage you to think about how you could take this and apply it in your own use cases, because there's plenty of services that you have no control of, but you can inject this type of functionality. One that I was playing with was, are you guys familiar with Redis? It's kind of like the new rage now with the databases. It's really fast, it's really awesome, supports all kinds of neat operations on lists, basically a more interesting memcache. But I think you could actually build all that functionality with an intercepting proxy and memcache, because nothing stops you from implementing all of those same commands with multi-gets with memcache. Just a thought. Same thing for authorization, and encryption, decryption, and all that kinds of stuff. So play with it. It's cool. That would be it. So any questions, thoughts, ideas?
Yeah, I'd like to give back to the production staging environment, direct practical staging. How did you deal with new features? Because obviously every new feature would therefore be a bug.
Yeah, so in our case, this is not the solution for every problem, though. I think it almost is. Specifically, we use this for newer versions of existing services where we had some consistency. I'm not sure how you would do this against, let's say, 2 different Rails applications with different feature sets. I'm not sure if that would work at all, in fact. Really, the point of this for us was we have an incremental update. So in our case, it would be a faster implementation of a ranking algorithm or something like that, where we really wanted to see, that this new library give us a plus 5% or minus 10%. And that kind of, when the difference is so low, it's really hard to simulate a consistent workload, right? So we just punted on that altogether and said, let's just play production traffic, and that'll be the decider.
Can you elaborate a little bit on the idea of charting MySQL? Did you try it already, or were you just
No. Yeah.
Like where would it be at the data packs record?
Right. So the question was, have we played with the idea of sharding using this technique? I haven't done anything with this model. You could do it. There's nothing stopping you, right? Because it's just a TCP layer broker, essentially. In some ways, I think you'd be kind of crazy to do that, because that's exactly what MySQL proxy is for. So the only reason why you might want to do it in Ruby is because it's in Ruby, versus MySQL proxy, you're learning Lua all of a sudden, which is actually a pretty nice language too. But I haven't tried it, so I can't say. But the thought would be just to inject it right in between your database and your client, and then you have it's basically a text protocol, unless you enable compression in your MySQL client, that you could just look at and say, well, let me pick an example. Let's say you're requesting a photo, right? And you have an ID on it. So you just define a sharding function on the ID, and you say, well, that's database number 5, so I'm going to go there. I think that would be actually fairly easy to implement. Right. Well, yeah. You're just making a decision for where you actually want to send it out to. You could do rewriting as well.
Does Event Machine have anything analogous to Twisted's protocols? I mean, in the example of MySQL, you need something that understands the MySQL protocol. Same thing for Memcache, for HTTP. So if you're going to write a proxy, it becomes easier.
So Event Machine is basically the translation of Twisted into Ruby land. So if you look at the examples provided by Twisted, they're also provided in Event Machine. So there's an SMTP client, HTTP client, all kinds of stuff. I wrote one for HTTP called EM HTTP request. There's a number of different implementations. There's AMQP, XMPP. Basically, there's almost anything under the sun. I'm not going to claim that they're all 100% complete, but basically for anything that you're going to think of, there's something already there. There is actually an EM MySQL driver, which uses Event Machine. And I think Amanda's here in the crowd, so we can talk to him about that.
You're using this to test the staging and else, I mean, performance, I would think, unless you're trying to do your database first, otherwise the same machine getting a lot more hits, twice as many hits, but you're getting, they're both running in process, so I think that would impact on the performance.
Right, so that's a really good point, right? So we're adding, essentially we're doing a +1. So if we had 5 servers before, we added a 6th one, and the 6th one is purely overhead, then it could be the case that those 5% came from the database. And that's absolutely true. In our case, we actually defined our databases as another service layer, and we have pretty good feeling that adding another application server is not going to have a significant performance impact. So it's a really good point.
This is a question related to your actual staging and production Duplex part. How did you benchmark that? I mean, where you actually had the Proxy Server taking a request and then spitting them out to, you were testing a production staging for benchmark. But what about the actual Proxy Server? What are the benchmark numbers for that? How many requests could you handle? Was there a throughput bandwidth issue that you?
Right. So I guess the question is, how do we benchmark the actual proxy itself, right? What are the characteristics on that? That's a funny one, right? Because there's really nothing you could test. Some data points are very, very basic implementation of event machine connection. Will give you on the order of magnitude of a couple of thousand requests per second. In our case, none of our actual APIs would respond in maybe 200, 300 requests a second, so we knew that wouldn't be the bottleneck in the first place. And then for the actual overhead, we did measure it. By just sending a consistent stream against one of the application servers, we found that the performance hit was about 5%. And that's strictly in the fact that you have to establish yet another connection along the way. Right? But for our purposes, 5% wasn't all that bad. And at this point, we've injected a bunch of these intercepting proxies or transparent proxies full time. They're running always in production, and we basically have a flag to just enable or disable them. Yep.
Excuse me. We're going to have to wrap up.
Okay.
If you have more questions, you can come find Ilya on break. Thanks very much.
Thanks, guys.